the metabolism of alcohol is really super easy. But what we're going to talk about is alcohol consumption and metabolism in both the fed and fasting state, because that is where medicine is important. In the fed state, we're going to see how it adds to our caloric positive energy balance, and in the fasting state, we're going to see how it leads to the issues that alcoholics have to deal with. Okay, so what do we do with ethanol? Well, ethanol has a very easy metabolic pathway. So the first thing we're going to do is we're going to consume our ethanol. And ethanol is very well absorbed through the lining of the gut. So there's no transporters necessary for ethanol. It just diffuses by passive diffusion inside the body, into the circulation. And hence why, if you're on an empty stomach and you don't have anything to dilute that alcohol when it hits your stomach, you can get a buzz from alcohol real quick because it's absorbed by the stomach lining by passive diffusion. So now it gets into the circulation, and then the liver is responsible for detoxification. And the first thing the liver is going to do is convert this ethanol into acetaldehyde. And this reaction is going to generate NADH. So it's going to generate energy. And the enzyme that does this is alcohol dehydrogenase. Now, the reason I put this up here, converting to NADH, is because there was a long theory for a very long time that ethanol really did not contribute to the body's energy production until this pathway was discovered. And then it was discovered that ethanol actually does have caloric content, primarily because you can break the ethanol down by oxidative reactions and generate NADH. And of course, NADH, we know, can be used for generating ATP. So this is the caloric content in alcohol. Now, when people say it's empty calories, what does empty calories mean?
No nutrients.
No nutrients, yeah. There's no nutrients in here. You're not getting any carbohydrates, you're not getting any protein, you're not getting lipids. Most important for alcoholism, you're not getting any of those, plus you're not getting vitamins. You're not getting the proper minerals and vitamin components on here. So that's what's typically meant by empty calories. That doesn't mean it doesn't have caloric content, though. Now, at this point, the acetaldehyde is going to be translocated into the mitochondrial matrix. Once we get into the mitochondrial matrix, we have another enzyme that is called acetaldehyde dehydrogenase, and that is going to convert the acetaldehyde into acetate. Now, this being a dehydrogenase reaction, again, we are generating, on the second step of alcohol metabolism, we're generating more NADH. And again, the reason I'm doing this is to impress upon you the amount of energy and caloric consumption that alcohol has. 1.5 ounce shot of hard liquor has about 100 calories in it. There's quite a bit in here. So now the acetate has two different directions it can go. The first direction is it can go into the circulation secreted by the liver. Of course, all of this is done in the liver, the detoxification of ethanol. Once it gets into the circulation, now pretty much all cells can take this up. The primary cells that will use this, of course, is our goat, muscle cells. The other path for acetate is to stay in the liver and be converted to acetyl-CoA. Same thing that's going to happen to muscle. The acetate that it picks up is going to be converted into acetyl-CoA. The enzyme's called acetyl-CoA synthetase, not important, you know that, but just know that the acetate is converted into acetyl-CoA. Now, what does acetyl-CoA do? Goes into the TCA cycle, right? And in the TCA cycle, we are going to generate 3 more NADH plus 1 FADH2, which of course goes into the electron transport chain and ATP synthesis. So we're talking here 1 molecule of ethanol generating a total of 5 NADHs and 1 FADH2. That's an enormous amount of energy for 1 molecule of ethanol. Now, what's important here also is this intermediate, acetaldehyde. Acetaldehyde has 2 functions. The first function is to cause liver damage. Because it's an aldehyde. And remember, the aldehyde groups on the end of molecules, aldehydes are very reactive. And so these are so reactive they will bind to just about anything that is available with electrons to bind to. So for example, these aldehydes can bind to hepatocyte proteins, damage them, and inactivate them, causing compromised activity. They can also bind to fatty acids, so they can damage membrane structures. So the chemistry of aldehydes is rather nonspecific, but it's very potent for damaging proteins. Okay? So this is the primary molecule when we talk about liver damage. Ethanol is going to be processed rather quickly. We want to process the acetaldehyde as quickly as we can, but all of these other compounds down the way here, acetate, acetyl-CoA, these aren't very toxic because the liver has a way to get rid of them. So it's the acetaldehyde with that reactive group that is responsible for liver damage and ultimately cirrhosis over long-term alcohol use. Now, the other thing with acetaldehyde, and this is kind of a mixed bag, it's a good thing and a bad thing. What does acetaldehyde do to your constitution? Remember that one? It makes you feel nauseous. It makes you want to vomit. Because the acetaldehyde is a toxic compound. And our chemical sensing up here in the brain that Dr. Shuttleworth was talking about will recognize these aldehyde compounds. And as these aldehydes start to leak out in the circulation, this is what's going to cause our hangovers. So it's the excess buildup of acetaldehyde. So this compound, how is this compound used clinically? How is this acetaldehyde taken advantage of in a clinical sense?
You can treat alcoholics with it.
Yeah.
Give you Ethanol.
So if... You ever heard of that drug? This will inhibit acetaldehyde dehydrogenase. So if you provide disulfiram to a person, you inhibit this, what is that person going to experience? Hangover, nauseous, vomiting. So as soon as you take a little bit of alcohol, you start feeling absolutely horrible. Start feeling like you want to retch. So those are kind of the ethics questions that I've seen a question similar to this in the NBME database. And that gets at understanding what this particular drug does to inhibit this enzyme to cause this effect, and the combination is an individual is going to require alcoholism counseling.
Yes.
Now here's another. How was this discovered as a target to try to treat alcoholism? Well, there were studies done, genetic studies, and they looked at individuals that had increased activity or increased amounts of these enzymes, of alcohol dehydrogenase and acetaldehyde. And what they found is that these individuals had an increased level of alcoholism because they had to take more alcohol to get that social effect, because their enzymes were so hopped up that they were processing through this pathway so quickly. So that ended up turning them to a higher amount of alcohol consumption to get some sort of effect. Now, opposite, there are individuals that have reduced acetaldehyde dehydrogenase levels. Reduced levels. So genetic changes that reduce the amount of the enzyme or the activity of the enzyme. How many alcoholics have been discovered in this population? 0. Alcoholism. 0 cases have been identified in populations with mutations in this enzyme. And that's because the slightest bit of alcohol will cause those side effects. Okay? Now, let's talk about ethanol metabolism in the fed and fasting state, because this is where it really makes a difference. So last night, I had a nice big dish of pasta with some nice spices, little pesto, olive oil, of course, just sun-dried tomatoes. Did that put me into a fed state?
Oh, yeah.
Oh, yeah. What was my primary energy source I was consuming?
Glucose.
Lots of glucose. Okay, so I went into a fed state equals insulin secretion. So that's the first thing that happened. I had to wash this down with a proper vino. And so actually last night I had a Merlot. And so that Merlot was added on top of this in a fed state. Now, what happens metabolism-wise? The carbohydrates coming in to the liver will go through glycolysis and produce pyruvate. Being in a fed state, the first thing the pyruvate's going to do is it's going to enter the mitochondria and convert to acetyl-CoA and make ATP. Now, in parallel, what is the ethanol doing? That is being converted to acetaldehyde. That translocates into the mitochondria, and this is going to be converted to acetyl-CoA through the acetate metabolism in a fed state. Now, the pyruvate is also being converted to acetyl-CoA. So now I have so much acetyl-CoA coming in, the TCA cycle will have a maxed out NADH. So the concentration of NADH is going to be really high because we're making a lot of NADH from all of this acetyl-CoA going into the TCA cycle. Once this NADH gets high enough, what's going to be inhibited? PDH is going to be inhibited, but what in the TCA cycle is going to be inhibited? Isocitrate dehydrogenase. So once that is inhibited, the TCA cycle is really going to slow down. So the isocitrate is going to go backwards to citrate. Citrate cannot go backwards to make oxaloacetate and acetyl-CoA because that's an irreversible reaction. So what happens to citrate? Fat, yeah. So both of these will be formed into citrate, and then the citrate exits into the cytoplasm for fatty acid synthesis. Now, under these conditions, under the fed conditions, this is going to be promoted, of course, because we have insulin signaling. And insulin is going to activate what enzyme for fatty acid synthesis?
Acetyl-CoA carboxylase.
Acetyl-CoA carboxylase. So with one glass of wine, I am going to be increasing my fatty acid synthesis. Now, after I do this, what's the fatty acid normally going to do? What are we going to do with this? In the liver, in a fed state. Triglycerides? So now we've got triglycerides in the liver. What do we do with those? Do we store them? We're not going to store them. We're going to combine these with cholesterol. And what's the protein? We're going to construct a lipoprotein. You're scaring me. ApoB100. And then we're going to make and secrete VLDL. And VLDL now is going to circulate through the body, providing fatty acids in the form of triglyceride hydrolysis. What other tissue is going to really like to grab fats out of this? The heart. Heart for energy. So drinking wine is good. I just justified it. Thank you.
Adipose tissue.
Yeah. What's this thing here?
Your love handles.
My love handles, yeah. It's the part on my motorcycle. It jiggles and it makes me realize that I gotta watch my diet.
It's for your white bubble bun.
Yes, exactly. That's for your passenger, for your door. So this is gonna go to adipocytes. Now this is all perfectly fine, right? You get a little bit of all this enjoyment up here, and you get a little bit of adipocytes formed. Now, what happens for those individuals that like to drink, say, a couple of six-packs a week? But for guys that have this beer belly, how do they get this beer belly? They're pushing along a little harder on this pathway, right? They're consuming food, normal carbs and normal calories, and they're consuming more alcohol. So they're just going to be pushing more down this pathway with more fatty acid synthesis and more developing into adipocytes. Now, as you increase alcohol consumption in the fed state, is it possible to saturate this pathway? What part of the pathway is going to become saturated? Assuming you're not drinking so freaking much that you're blocking this and causing a buildup of acetaldehyde.
Acetyl acid carboxylase.
So acetyl-CoA carboxylase will continue its activity. Will this be inhibited because you've accelerated the enzyme with insulin? Where would the block be? Yeah, right here. You're saturating the process of constructing triglycerides and VLDL. So if this is blocking, where are those things going to go? The fatty acids and triglycerides, if you're saturating and you're not getting the VLD out as fast as you possibly can. What's that going to lead to? Steatosis. And so this process here is alcoholic fatty liver. Okay, so we saw fatty liver before, which was non-alcoholic fatty liver. And in this case, this is alcoholic fatty liver primarily because it's the extra acetyl-CoA that's being generated from ethanol driving this process. Now, histologically, would this look any different than non-alcoholic fatty liver? Nope, look the same. It'll look the same primarily because you're looking for those enlarged hepatocytes with those clear zones in there, which is the stored fat inside the hepatocyte. Okay, so that's the fed state and how we can process the ethanol, how it increases our fatty acid synthesis, and how that increases not only weight gain, but it can also lead to alcoholic fatty liver disease. Now, what about the fasting state? So the fasting state, we don't have any carbs or fats or proteins. What we have is ethanol. So the first thing the alpha ethanol is going to do is what we saw before. This is going to increase the amount of NADH in the cytosol. This acetaldehyde gets translocated to the matrix of the mitochondria. It forms acetate, making more mitochondrial NADH. And then the acetate is converted to acetyl-CoA. So in the fasting state, we have the same metabolism going on, but the response by the liver is going to be very, very different. So in a fasting state in the liver, can we do this? Can we convert in a fasting state in the liver the acetyl-CoA that's generated from ethanol metabolism, can we use that to make fatty acids? Okay, most of you are saying no. That's true, because this is blocked. Fatty acid synthesis is blocked. Why is fatty acid synthesis blocked? What's the mechanism? Glucagon signaling. So glucagon is doing what? What's the enzyme that is the entry step into fatty acid synthesis? Acetyl-CoA carboxylase. And the glucagon is causing this to be phosphorylated and putting this to be inactive. So now the acetyl-CoA that's left here, if we're in a fasting state in the liver, can we do this? Can we take that acetyl-CoA from our alcohol and can we make glucose from it? Acetyl-CoA under no circumstance can be used to make glucose. So this is not going to happen. So with rising amounts of acetyl-CoA, that means that we are going to inhibit PDH, And that's going to force this reaction of pyruvate into oxaloacetate. This is pyruvate carboxylase. And the acetyl-CoA is going to activate this. Okay, so this is just acetyl-CoA coming from excessive alcohol consumption in a fasting state. Now, this looks like that drinking alcohol can promote gluconeogenesis. So then this converts to malate, and then this out into the cytoplasm. So it looks like it can promote gluconeogenesis simply because you're increasing the amount of acetyl-CoA, which is turning your pendulum here to turn off PDH and turn on pyruvate kinase. So any pyruvate that's available can be used to make glucose. So the pyruvate in a fasting liver, is that coming from glucose oxidation and glycolysis? No, because glycolysis is shut off in the fasting state in the liver because we are doing gluconeogenesis. So where's the pyruvate coming from? Alanine. This is our transamination reaction with ALT. And it's also coming from lactate, from muscle, by lactate dehydrogenase. Now, in order to have lactate move into pyruvate, what is the cofactor that we need to perform this oxidation reaction? NAD. So remember that lactate needs an electron carrier to make NADH to give you pyruvate. So in skeletal muscle is taking pyruvate, red blood cells are taking pyruvate and they're shifting this into lactate to keep generating NADH for glycolysis. The liver under normal conditions takes the lactate up and reverses this direction so it can use those carbons for gluconeogenesis. Now if you've got a lot of alcohol and you're generating a lot of NADH, what is your NAD concentration going to be like? Look, it's going to be really low. Yeah. So how is this reaction of lactate to pyruvate going to work when you need NAD and the concentration is low because of the ethanol oxidation? This reaction will be blocked. So that means that the lactate that the liver is taking up from the circulation is not going to be able to be used for gluconeogenesis. Now add on top of that the additional problem that with high levels of NADH, the hepatocyte's going to want to get those levels down so it has more NAD available. So how about if we take the pyruvate that we are generating from alanine transamination and take pyruvate and convert this back into lactate. So it's a twofold effect on pyruvate. So not only are we not generating pyruvate for gluconeogenesis, but whatever pyruvate we are generating from alanine transaminase is being converted right back into lactate. So under these conditions, what's going to happen inside the liver of the concentration of lactate? It's going to go way up. And the liver can transport lactate because it can transport it in, it can transport it out into the circulation. And high levels of lactate in the circulation lead to what medical problem? Lactic acidosis. So that is one avenue of excessive alcohol consumption in a fasting state in the liver. So it's simply because of this extra energy in the ethanol oxidation that it's driving this reaction in the wrong direction between the pyruvate and the lactate. Now that's not all, right? What's the other source of acetyl-CoA in the fasting liver?
Ketones.
Beta oxidation.
Oh, source.
Of fatty acids coming from what tissue? Adipocytes. Under what hormonal stimulation? Glucagon. So our acetyl-CoA levels are going to really go up fast because oxidation, if we have a C16 fatty acid, that's 8 acetyl-CoAs. And with all of this ethanol coming in here, adding to this acetyl-CoA, the concentration of acetyl-CoA goes up. What's that going to generate? Ketones. So the ketone synthesis goes up, concentrations of ketones skyrocket, these enter the circulation. And what medical problem is from that? Ketoacidosis. So it's this effect of why I like to say that our moms, before you go off to college, your moms warn you about, now don't drink too much with your friends. All mothers know this metabolism. They really do, and they know the problems that occur from this. Okay? So we have a problem with lactic acidosis. We have a problem with ketoacidosis. What's the other problem we have?
Acetone.
We have acetone. Yep, we got acetone formation because of the spontaneous decarboxylation of acetoacetate. If lactate is being produced from pyruvate, what is your gluconeogenic activity like?
Diminished.
It's really diminished because pyruvate is a major carbon source for feeding into gluconeogenesis. So if the pyruvate is being taken away because it's being converted to lactate, how much glucose is this liver making? Not much. What medical problem does that lead to? Hypoglycemia. So now when an alcoholic comes into the ER, and they're staggering in there, you know they're probably malnourished. So they're probably lacking fuel and they're probably lacking some important vitamins and cofactors. We'll talk about those a little bit. But they're under heavy acidosis, metabolic acidosis problem, and they're also suffering from hypoglycemia. So it's a multiple problem that these people are having with ethanol consumption in a fasting state.